Okay, so I also would like, first of all, to thank Hussein for putting together this wonderful meeting here and for inviting me and giving me the opportunity to talk about my work that I essentially started here at ITAMP, but then also continued afterwards. So there's kind of some people here at ITAMP which I also continue to work with. Then there was some continuation of this type of ideas in Innsbruck. And now, since about 1.5 years, I'm at the Technical University in Vienna, building up my own group. And there are also some people, like my PhD student here, Cosmas, who is continuing these ideas on kind of nanomechanical, optomechanical systems that kind of Jake already introduced. So I will kind of continue along these lines, maybe emphasize some points once more that Jake has already mentioned. So in this talk, I will explicitly focus on nanomechanical oscillators. So if you're not very familiar with this field, I mean, in principle, it's just small objects, small bars vibrating, so either bars or membranes, and the typical are in the dimensions of a few micrometers, and this means they have mechanical frequencies in the megahertz, maybe up to gigahertz regime, while at the same time, they're still incredibly high quality factors, so they're incredibly well isolated from the environment. So the reason why people actually in the beginning, I mean, this field is not very new, but why people actually started to look at these devices is that these resonators respond very sensitively to static or oscillating forces. And because they are nanofabricated object, you can functionalize them. So you can put a mirror there, you can charge them up, you can put small magnets, and by this, these oscillators respond very sensitively to essentially all type of forces. And this response, so if we apply a force here on the oscillator, it converts it into displacement, and then you can use on the other side, I mean, the most sensitive method to detect this displacement, which are usually either optical or electrical readout devices. And the whole thing, ideally works with at the same time adding very little noise. So this kind of basic concept led to the development of these nanomechanical oscillators, to do different type of sensing, and most impressive is maybe also this mass sensing, where people now sense individual atoms using these resonators. So here's an example from Dan Ruger's group, where he used this oscillator to sense a single spin, by simply looking at the vibration or the force back action on this cantilever. And there are also, in every cell phone these days, there are some electronic components which are really based on mechanical elements. So this is, I think, a really interesting field on its own. But what kind of happened at the kind of time when I was here at ITAMP, so this was, I forgot to mention in the beginning, so it was 2007 to 2010. Around that time, people developed now active cooling mechanisms. So it's kind of laser cooling, so similar to cooling the motion of atoms. They used kind of now laser cooling techniques to actually take this object and cool individual modes close to the quantum ground state. Okay, so this really happened around 2008. I think there were the first experiments, and then now 2010, 2011, the people have really shown that you can take these devices, which you still can almost see with your bare eye, and now the vibrations, so the fluctuation here, are no longer determined by thermal fluctuations or some other noise. So they really determined by the 0-point oscillation of this mechanical degrees of freedom. And I think that's, in the end, quite amazing. And of course, now this opens really a new field of physics, where we can now look at quantum effects. So sorry about the laser pointers. Let me try this. So we can now look at finally can look at quantum mechanics, now no longer kind of what you used to. Okay, somebody a laser pointer here? So what you used to with atoms and iron, where quantum mechanics is well confirmed. I mean, people have scaled this up to bigger and bigger molecules. And this now, having now this mechanical system in the quantum regime would really allow us to do now quantum physics with really macroscopic objects, so 10 to the 10, 10 to the 12 atoms. And by this, on one, we can, sorry. Yeah, wonderful. We can.
May I ask you about the ground state issue in previous slide? No, don't return. Yeah. What's the H omega? What's the gap between ground and first excited state?
So it's So it's megahertz, so that's microkelvin or something like this. Yeah. So usually you cannot cool it down directly, but it's it's microkelvin. Yeah. Yeah. Okay. So, and the goal is, of course, I mean, by exploring this more and more, on one hand, okay, simply push our ability to see quantum effects now to larger and larger objects, and maybe at some stage even discover new physics. And I think that's what Jake kind of indicated also in his talk, I mean, this last slide, is that, even if there's no reason to believe that quantum mechanics breaks down, okay, there's no evidence that predicts this, we still, on the other hand, I mean, this quantum mechanics is tested on the scale of atoms and molecules, but nobody has really measured it or seen quantum effects at these big scales. Okay, so there's at least a reason to look for it. And the other point I want to make out, I mean, these objects, so once we get into superposition of these larger objects, at some stage we have to face the fact that at this stage we don't know how to combine quantum superposition with general relativity. Okay, so I mean, even though this is quite hard to see, we would see this effect. I mean, eventually, this is maybe a good system to go further in this direction and see that maybe eventually we really discover new physics along these lines. So the other aspect, so suppose you believe now in quantum mechanics and maybe now even on a short-term scale is, I mean, given these systems now in a quantum regime, can we actually use this for something? And here I want to kind of go back to this initial slide I showed about why these mechanical systems are useful for classical applications. And this is really that you can functionalize them and use them to couple them to different type of systems. If you now do the same thing in the quantum domain, you see that these mechanical systems can really function as an interface between different, for example, magnetic, electric, or optical quantum systems at the same time. And by this, they might have applications for quantum information processing or quantum-enhanced sensing applications. So now maybe to stress this point a little bit more, I actually want to start with a now simple example, and that's also kind of what I started here at ITAMP. And it's simply the question, I mean, how can we couple now this mechanical system, which is a big object, to something, like a microscopic system, like a spin-1/2 system or an atom. And the basic idea, which is shown here in this figure up here, is that we take this resonator, we apply a strong magnetic tip, or we attach it to it, and put it above the solid-state spins qubit, so some qubit which is localized in this, which I can localize, for example, an NV center, but in principle also any other spin. So what this means, I mean, if I place this tip now above the spin qubit, okay, there will be a Zeeman splitting, and now if this tip moves up and down, because there's a strong field gradient, now also the level splitting of this spin will change as a function of the position. And if I write this in a quantized form, I get some interaction Hamiltonian, there's some coupling constant, A plus A dagger simple position, and times the sigma C operator of this spin. And now the important thing, of course, is that there's this coupling constant, which means this is the level shift that the spin experience when this oscillator moves by a zero-point motion. Okay, so that's the relevant quantity. Now, of course, you can imagine that this is, is a very big thing, has a big mass. The zero-point motion is small. The magnetic moment of a spin is very small, so you don't expect this coupling to be very large. But actually, what it turns out, and this was also quite a surprise when you put in some numbers. So due to the fact that it can actually go very close, to these localized spin qubits here in solids, all the gradients, that actually magnetic field gradient can actually be very huge. And if you put in now some realistic numbers, you get coupling constants in the order of a few tens, maybe up to 100 kilohertz. And now what does this number mean? I mean, is this now a big effect? Is it a small effect? And to see this, you have to compare this now to the relevant dephasing or decoherence mechanisms. And this on one hand, the spin dephasing time, so the T2 time, and this can actually be much lower. So these days they're sub-kilohertz T2 times. And the other relevant scale is kind of the coupling of the mechanical system, which is well isolated, but still coupled to a phonon path. So there's still some small residual damping, and this damping, especially it's coupled to a high temperature reservoir. And this gives rise to a so-called thermalization rate, so which is KBD over h bar q. But if you now go to kind of Kelvin or sub-Kelvin temperatures and have these high quality factors, you actually find that this coupling can really exceed the main decoherence sources. Okay, so that's, I mean, in principle, it's just a simple estimate here, but it's important because it means that with this system, we can in principle have a strong coupling between a single spin, so a single microscopic system, and this non-mechanical oscillator.
So how large is the magnetic field gradient?
So it can, I mean, for this, if you do an estimate, 10 to the 6, 10 to the 7, and that's Tesla per meter. Yeah. So that's about what people have managed to do. So, for example, the Ruger group, they can produce these gradients. Okay, so what does this? How can we benefit from this coupling? And to see this, I mean, it's better to view actually this coupling not as a level shift, but kind of equivalent. You can think about this as a force. So this is just the x times, which depends on the state of your magnetic dipole. So suppose you cool now this resonator to the ground state, you prepare this magnetic dipole in superposition, you let this interact for a while, you actually generate out of the superposition of the spin, you generate a displacement, so kind of a little Schrödinger cat state of this resonator. So this by itself, okay, I mean it's a nice effect or a nice state, but I think the important thing is now that this is kind of, you know, as I mentioned before, it's a big resonator, okay, it's macroscopic. So I can engineer its properties, and in particular, I can also, you know, instead of having only a magnetic tip, I can also charge it up, okay? I can metallize it, I can put some voltage there. And by doing so, you know, this displacement now corresponds to a moving displaced charge. So what I get overall is that, you know, this magnetic dipole moment has translated into electric dipole moment, which in principle can be as big as possible as you want, you know, depending on how much charge you can put there. So this is kind of a basic mechanism which shows how this oscillator or this mechanical system can allow you to kind of amplify a small magnetic dipole moment in a big electric dipole moment. And if I now take, for example, two of the systems, you know, I place them close together, each of these spins will push this resonator, and these resonators will now interact via some strong electrostatic interactions. And by this, I can, you know, effectively engineer effective spin-spin interactions, which are no longer dipole-dipole, a magnetic one, but here are really mediated by this large electrostatic coupling.
That's a great question. So when you introduce this electric dipole, so you try to does it introduce other decoherence processes?
Yes. Yeah. Yeah. So I mean, this is of course now the simple picture, and just briefly mention. I mean, this was one of this paper I wrote here at ITAMP. I mean, then of course you can make it more flexible. Instead of coupling directly via free space, you can actually put electrodes there, and in this sense, kind of take your spins that are sitting there in the solid, and via this mechanical oscillator, you know, wire them up, and use now the electrostatic interactions to kind of control effective spin-spin interactions. So now, as you mentioned, I mean, there will be now, of course, the usual magnetic noise you have before, but there's also now electric, especially this 1/f noise, Johnson noise, and so on. And I mean, to make this whole thing work, I mean, you have to do different spin echo pulses, make these interactions kind of quasi-resonant, so that you really amplify this. But I think in this paper we did actually, most of the work was actually showing that it actually works with reasonable parameters. Okay, so I mean, this first part was kind of to kind of illustrate again. I mean, what could be the potential of these mechanical systems. Okay, so this is really what I think is also one of the long-term goals in this whole field. So to really use them for these type of applications. Now, of course, I mean, even if you do this here on a paper and make all type of estimates, I mean, it's still not trivial. Okay, so I don't want to say there's something you can do immediately. Misha's group, so Shimon, probably most of you know, they're really working on this thing, but it definitely will take a while to get there. So let me, therefore, think about, can we do something that maybe now gets rid of a lot of these complicated components and do something maybe simpler, that we can do right away. And for this, I want to now, consider again this mechanical oscillators and nothing changes. Except that I now want to focus on oscillators which are made out of diamond directly. Okay, what does it gain us? So we know that diamond is a very stiff material. So immediately by going from some silicon nitride or so to diamond, the frequencies are much higher, and for these micrometers dimension, you easily get, gigahertz phonon frequencies of these vibrational modes. Then what you also know is that the diamond is a very good conductor, which means that there's a low intrinsic scattering, phonon scattering rate, okay? So in principle, we expect that these diamond resonators have very high Q and should in principle be one of the best oscillators. So the reason why so far, or until very recently, nobody has worked with these diamond resonators is that it's, on the other hand, hard to fabricate them, okay? So even if they would be very good, we first have to produce them. And this was now a big challenge that now over the past 1 or 2 years, people have managed, at several places around the world. And now people can really fabricate these diamond resonators also with the expected high quality factors of up to 10 to the 6. So these things are now really available in the lab. But the most important thing is actually that these diamond oscillators, so they are not perfect, but they also have defects. And I mean, as I mentioned already before, and probably all of you know, in this diamond, the most prominent defect these days is this envy center, with essentially some localized electrons here in this nitrogen vacancy center. And if you look at the energy level structure of this defect, you find there's a triplet ground state. Okay, so there's ms plus minus 1 components and ms 0 component. And what people usually do is use this at least 2 states as a spin qubit and for magnetometry application. And these have a very long coherence time, even room temperature, and you can easily control it with microwave fields. But one should also not forget, I mean, this long coherence time and so on is not very special, okay? So there are many defects that could have these coherence times, but the most important thing about this envy center is that actually the right optical properties, so you can drive optical laser excited, and by this do some state preparation and also detection schemes. So what's now kind of different to kind of doing quantum optics with atoms and these solid state defects is that, they are embedded, so all the levels, they're embedded in the solid state matrix, so in diamond lattice. So if I now excited this envy center to some electronic states, there will be a lot of lattice vibrations. And in particular for this envy center, you find, I mean, if you do some excitation spectrum, I mean, you would have here the zero phonon lines, which corresponds to a kind of direct excitation. But then you have these huge phonon sidebands, so that they shift your frequency and they create excitations in the lattice. So this means that everything you want to do coherently, you want to sit on this zero phonon line, which only 5% of the total optical light scattered. So anything you do for quantum information processing, interfacing with light, so this is really the bottleneck of doing quantum optics with NV centers. But on the other hand, this means, if there are these huge phonon sidebands, you see that this corresponds to a strong coupling to phonons. And what is kind of bad for doing optics could be very beneficial if I want to couple these phonons, okay? So if instead of considering now some envy center in a bulk, I put this now in a diamond resonator, it will also couple to these localized, so these localized phonon modes, which are now, have very high Q resonators. So this would give rise kind of to now peaks in the spectrum, which correspond to individual, very isolated phonon modes. Yeah.
About symmetry, why you have only one localized phonon mode? Why? Because symmetry it seems too complicated. You may have several one here, but you have one single.
Now, phonon modes you mean, or? I mean, here this is this.
Localized from the peak here, first localized port which you have.
So this is the zero phonon line. Yeah. So this corresponds to exciting the system without emitting phonons.
No.
Okay.
You have absorption with absorption phonon, not only emission here. You have a temperature, you have absorption of.
Yeah, I mean, okay. So if I find a temperature, there would also be some excitations over here. You mean this? Yeah. Yeah. Okay. So this is kind of illustration.
So low, you don't, but unusual temperature which you show, you have absorption and emission of phonon kind of.
Yeah. So this would correspond to the low. It's just illustration. So this is would correspond to low temperature case. Okay, but kind of the point I want to make here is really that I mean in principle we have this strong coupling to phonons that people see in the NV center, and what is really a nuisance here for many optical experiments can be actually very beneficial to couple here to some isolated phonon modes in such a resonator. And the question now we can now ask, I mean, given this strong coupling, I mean, can we do something, for example, combine this now with laser excitation and do something like laser cooling? And here one has to, really point out this this nice work here almost 10 years now ago by ITAMP, who first proposed this strain-induced coupling laser cooling for, in this case, it was a quantum dot embedded in a nanoresonator, but in principle the scheme should work very similar here. And the other question is, of course, I mean, if I have this strong coupling to phonons, I mean, can I use it then again to do mediate some spin interactions, at least within this resonator? So to answer now this question, is this at all feasible? One actually has to do a little bit more detail on the electronic structure of this NV center, and just a very basic, just the basics. So this NV center, it has this C3V symmetry, and if you now fill up, these different orbitals, you actually find that there's a ground state, which is a spin triplet, and then if you excite one of these electrons to this AE state, there are actually two possibilities, so two principal degenerate excited state that are this usual transition here that we use. So both of these states are triplets. So if I include the spins, in principle I have now additional splittings. In the ground state, this is this usual zero field splitting that people use to encode a spin qubit and drive it with microwave frequencies. And also in excited state, you have some spin orbit and spin-spin interaction that give rise to a few gigahertz splitting. I mean, for the following, you can actually ignore these states. I will actually assume that we start kind of in a MS equals 0 state. And as long as I apply only linearized polarized light, I will couple also in excited state only to this MS equals 0 state, at least to a very high fidelity. So the basic thing we have now in this NV center, so we have a one ground state and kind of these two electronic states, which in principle are completely degenerate. So now, of course, I mean, if I put this NV center in a usual solid, and in particular in this nano beam, so what happens if this beam now moves up and down? It will kind of stretch or compress locally the lattice. So what it of course means, I mean, this is exaggerated here, but it means, of course, that we break this symmetry. So now different things can happen. Okay, so first of all, I mean, there's always, in any lattice, there's always some static strain. Okay, so this degenerate is always lifted, and typically one finds, even without anything else, that there will be a few gigahertz splitting between these two states. So then on top of it, I have now this oscillator which creates some oscillating strain. And again, it depends now if the strain fields have some components which are conserve the symmetry. This would mean that these states move up and down together. If they break the symmetry, these states can move in opposite direction. And in particular also this if I apply the right strain direction, actually can couple these two states via the strain field. Okay, so the general type of interaction I end up with in the system is really that I have now this kind of three basic electronic states. There's some intrinsic level splitting up there, which I can tune with even also with electric fields. And now these upper levels are now coupled to my mechanical motion, and with this type of different processes, and again proportional to the elongation of this oscillator. So the thing is now, so again, we have here some more complicated coupling, but overall there's of course now the question, how strong is this effect? Now can I do again a simple estimate, and I think that's also given basically also in Atta's paper. I mean, I think you have similar numbers over there. So we can take a resonator with typical dimensions with a few micrometers. So as I mentioned before, I mean the frequencies here are very high, so in the order of, in this case, about 3 gigahertz. But also the coupling, you now see, this coupling, which was, a few tens of kilohertz for the magnetic coupling, can be now substantially larger. And we get typical values of 10 megahertz, maybe even a little bit more. So this means, first of all, okay, this sounds very good, but one also has now to keep in mind that these are electronic excited states. Okay, so they have radiative decay, and this radiative decay will be kind of on the same order. So this means we have kind of this regime where this lambda is quite strong, but maybe at this stage not super strong. But what is important here, that this lambda and both lambda and the decay are much larger than the mechanical dissipation rate. Okay, so we can still, using this guy, we have its potential that we kind of kick the resonator with this NV center, and before it can relax again or damp out, can really manipulate the state of the oscillator. So the general scheme we have now, and this is now a little bit different representation of this whole thing. So I'm not sure what I'm doing wrong. It's dying out. The laser pointers. Yeah. Okay. Yeah. Okay. So what I have here is again, so here this is my mechanical oscillator, and it's naturally coupled to some some reservoir, and this let's assume that it's a few Kelvin, so we don't want to work at room temperature, but it's not ultra cold, and at these frequencies, this still means that there are several hundred phonons in this oscillator. So on the other hand, I have now this coupling to this envy center, and as I mentioned before, this coupling, so there's this decay rate. So if I laser drive now this envy center, the decay rate actually will be similar or even faster than this coupling. So essentially, this there will be some excitation here, but this kind of envy center will relax always to a steady state on a time scale which is much faster than this coupling to this mechanical oscillator. This is now kind of the typical situation which you are familiar with from laser cooling. So we have some internal dynamics which is much faster than some change of motion of an atom. And this essentially means that this degree of freedom I can eliminate, I can treat as an effective environment. Okay? And in the end I end up with a picture where I have now this mechanical oscillator coupled on one hand to his his support, so the real environment. And then this envy center can be modeled as an effective environment with some cooling rate, some heating rate, and overall some effective temperature. And now the thing, of course, is that, and that's the main thing about laser cooling is that this T effective had nothing to do with any thermal equilibrium or so. So this is purely controlled by my laser detunings, Rabl frequencies. So really by my laser parameters. So a difference now compared to atomic cooling. So if you cool an atom, you usually don't care about the time scale where it cools down to zero. So you usually only care about the final temperature. So is it Doppler limit? Is it sideband limited? With these mechanical systems, you have to compete. This cooling here has to compete with the rethermalization rate on this side. So also matter is to not only go cold to low temperatures, but also do this sufficiently fast so that they compete with this rethermalization. So let me now briefly show some examples of what do we get for this system, okay? And so I simply now, again, take this level system, I switch on a laser, I have a certain laser detuning, which I define from this delta L from this lower state here, I have some intrinsic splitting delta here, and now I simply run the system and plot the final phonon occupation number as a function of these two detunings. So the blue side here, so the blue spots here correspond to cooling. And let me first actually focus here on this line. So it's very light blue here, so you probably cannot even see it. But so if I focus on this transition, so this means, so delta minus the mechanical frequency. So this means in this regime I have this situation where my laser is kind of red detuned to this first excited state, okay? So the other state is simply far off, it doesn't play a role, so it's independent of this delta. So this is kind of the situation that really now corresponds to this mechanism that has been identified here by Ignacio Wilson-Ray and Attach and Peter, and corresponds to kind of sideband cooling, where you apply a laser photon, it has lower frequency, so it needs to extract the energy of the mechanical motion to be excited, and then decays down. And each time, okay, it removes the phonon, so in the end you will cool down. So, but you see that already here this actually, even this works, but it's actually not a very strong effect in the system. And the reason is that to have this sideband condition and for a very high frequency oscillator, you need to be very far detuned. Okay, so the excitation of this whole envy center is very small. So on the other hand, we have this additional cooling peak here, which is much stronger. And if you think about what's happening here is that actually here the laser is on resonance, okay, so it's delta L equals 0, so you excite this low state. And what happens is now that this energy splitting here is in resonance with the mechanics. So what happens now here, you resonantly excite the system, and then a phonon can excite it to the other state, so this X level, and then it decays. And just to illustrate why this is now much more efficient, so if I do a quick estimate of the cooling rates I get for this scheme and for this scheme, Actually, the two rates scale as mechanical frequency over gamma squared. And now, again, because we are having here diamond resonators, with gigahertz frequencies, I mean, this is a few gigahertz, this is 10 megahertz, so typical numbers, this can really be a factor of 10 to the 4. And that's why I think, this degeneracy which we have here for the NV center, kind of for free, is really kind of a crucial, makes this a special system to actually to look for these cooling effects.
So this resonant cooling limit, Rabl frequency has to be less than gamma.
Yeah, so this expression is now for small omega. Yeah. I mean, in principle, you can also amplify this scheme by simply pumping more laser power, okay? But in the end, this will then mean you need a factor of 10 to the 4 more power, and then other things happen. Okay, so a second point I want to make here in this level diagram, okay, I mean, this would be ideal for ground state cooling, but now you see also all these red spots, which actually mean that the system is heated up. And if you think about this condition over here, for example, this simply means that here we have the reverse process, okay? So now the laser is actually, again, resonantly tuned to this Y level, but this Y level is now higher than this X level. Okay, so what it means, you excite this, it emits a phonon, goes down here, and decays back. So this constantly puts energy in the system, and we know from optical modes, if you pump energy into optical mode, eventually it starts lasing, okay? So here we can observe a process which is the equivalent one, so which is kind of a phonon lasing effect. So if you look at the occupation number as a function of driving strength here, so you see that the occupation number goes considerably up, and at the same time the statistics of this field, goes from thermal to a coherent state. So now you might ask, okay, why do you need a phonon laser? Every guitar string is in principle a phonon laser, more or less. But I think the relevant point here in this case is actually that, by scanning your beam, in this region, you kind of, by probing your system, you at the same time amplify it, okay? And if you're, at least in the beginning, you want to see this effect, you want to see the coupling of phonons, so this would be, ideal way to, not only observe it, but at the same time amplify this effect. So with this kind of the summary of this second part was, okay, so, having this kind of intrinsic coupling to strain in these diamond resonators would actually be a quite nice way to really have this resonantly enhanced or very strong phonon type of interactions. We can use this to do ground state cooling or kind of laser phonon lasing schemes. And in principle, you see a lot of other features. So this could also be at the same time be used to probe higher order phonon processes in the system, which at this stage are not studied in detail or cannot be studied in detail yet. So because I'm running out of time, that would be a kind of a last part, but maybe I simply skip this. So another project we worked on is now kind of looking at the same type of strain coupling, but now in the ground states, on the spin levels. You'll find that there's also, some effective strain-induced coupling between two of the spin levels. And although the coupling here is now much smaller, because, it's not electronically coupling to the lattice deformation, you can actually do, couple to many spins, okay? So kind of collectively enhance this effect. And by having many spins coupled collectively to a cavity mode, we know also from the experiments from Rabl and Vulitic, by doing this in an appropriate way, we can actually engineer collective spin squared interactions. And this type of interaction corresponds to a squeezing interaction, okay? So by having this type of G-square system, things in the system, we actually can take a spin coherent state, which has a certain width, and kind of squeeze it along one direction. And this is one of the, let's say, main effects by kind of quantum mechanics. So this spin-spin correlation can actually be used to enhance magnetometry applications. And I think in particular in this connection of NV centers as local sensors, I think this would be a nice application where you can usually use these phonons to couple to a few 10 or 100 spins and really induce quantum correlations. It could be useful for magnetometry. So for this, I think very briefly the conclusion. So something that also Jake has in principle mentioned, and I want to emphasize again. So over the past years, and now kind of being today or the last 2 years, we really have now this kind of new quantum degree of freedom in the lab. Okay, and I think that the field is not as large as ultra fast or ultra cold, discussed yesterday. But I think that this system will become more and more important in quantum optics and solid state communities. And I think also here at ITAMP we will hear much more. And finally, I showed a few examples, and on this slide, actually, I just want to mention that yeah. So you see from these dates, I mean, actually, so I left ITAMP around 2010. So what I want to emphasize here that many of these projects, were done afterwards, and I think that's also a very strong part of ITAMP. We have all these frequent workshops, the continued collaborations, and I think not only as a postdoc you benefit here from being here for 3 years, but also then from there on for all the ongoing collaborations. So thank you for your attention. Silly.
I have really two questions. One very simple about the quality of resonator, diamond. Because this phonon lasing, very interesting if you have a long living phonons. If resonator not good, they will die, they will have a disc or something like this. When you introduce NV center, you just automatically produce scattering or kind of corruption of your phonons. How important it is or not? Did you check after this quality of phonon spectra or something?
Yeah, I mean, in principle, we have a scatterer, but it's kind of very off resonant, so it doesn't do anything. And I just want to mention, I mean, these quality factors, these are measured quality factors 10 to the 6. I mean, these of course have been produced with diamond, which has NV centers and probably also many other defects in there. So this by itself doesn't limit it on the level of Q10 to the 6. And I think from diamond it's also known, that at low temperature the phonon scattering mean free path is actually limited by the carbon 13. So which you have 1%, and it has a different mass, and this actually, have been measured.
Not interfere with your lasing,
Yeah, no, I mean the lasing and these things have been calculated with this Q 10 to the 5, 10 to the 6, and these are kind of measured Qs. Now, what's limiting then? I don't want to speculate here, or I think it's not really known, but these are solid numbers that people can do.
Do you really need that high Q for phonon rating?
I mean, let's say for the ground state cooling, if you have this lambda 5, 10 megahertz, and then Q 10 to the 5 would give you kind of ground state cooling, and so cool down effect of 100. So in the other side, it would be kind of effect of 100, maybe 1,000 blown up. Yeah. So it's 10 to the 5 should be okay. Maybe you can see effects with 10 to the 4. So this is. Yeah.
Very, very clear. So the first part of your talk about this beam.
Yeah.
Maybe you could go to the slide. That slide. Yeah, I always have this question. We are talking about the mesoscopic system.
Next one.
Yeah.
Yeah.
That's right. We are talking about the mesoscopic system. Now you identify one particular degrees of freedom. Yes, in this case, a particular mode. You write a pure state of the superposition.
Yeah.
But the wave function of the system, of course, is not that. It's this one. In the simplest case, would be this one multiplied by thermal state. In fact, it's not a thermal state. It's a quantum really minimal state. Yes, but it's not a pure state for sure.
Yeah. I mean that let's say that the resonator has other higher modes. Okay. So and they would be usually in a thermal state. I mean, unless you also cool them.
Yeah,
but
in fact, it's more than that. It's because it's also the electron, the band structures and those things. So
But
this,
they highly excited. This electronic
no, this is very similar to many years ago. 20 years ago, maybe people were doing interferometry. That's the mechanical slits doing matter wave interferometry. Yes. There were speculations even, for instance, small living cells might go through, interfere. Yeah? In fact, I think they've done at MIT they tried. So then I think the largest thing people could do interferometry is buckyball, so it's not quite the size of 1,000 atoms, but 72 atoms.
Yeah, no, but I think they have progressed. So I don't know the actual numbers, but there are specific plans to do this with 10,000 or even more,
They
100.
already did
Alright, yeah.
experiments. 60 available, interferometry available.
Yeah, but these things, they will be really done. So I think they're doing it with kind of 1,000, 10,000 atoms right now, and they don't, everything is described by the center of mass motion. So there are a lot of internal degrees of freedom which are hot, and they don't affect this interference.
Well, I saw
Signal.
that they did the calculation, showed that the center of mass does give you the interference fringe, but there was a overall envelope determined by the other parts of the wave function being thermal. So if you don't cool them, eventually there's a limit beyond which you simply don't see.
I mean, but let's say I think we should.
Because it's our joint work with you. Maybe you forgot it. Yeah, maybe
Did we write anything? No.
it was article Bob for a USB. No, and we described this.
Oh,
Sodium something. You forgot it. Yeah. What we did in this system, when you do better wave interferometry, you have an overlap of wave functions. Yeah. Total wave function. I assume that they exist for entire world. When you have this overlap, you have a center of mass only 1 degree or 2 degrees. It's not important. But other degrees, yeah, they also include in overlap. If they are orthogonal, you have a 0. Even if you have some not important degrees, yeah, if they are orthogonal, you have a 0. Interference pattern will not exist. Yeah. This what, as I understood, Lee tried to ask you, how important is this for?
This,
Yeah, no, but,
responding to the
Maybe you should cut it here.
I suggest that we continue the discussion. Thanks very much.
Good.